you have a guest introducer. My name is David Pearson, and I'm a professor in the area of language and literacy and human development here in the Grad School of Education. And it's my privilege today to introduce my colleague and collaborator, Jacqueline Barber, who is up at Lawrence Hall of Science. And Jackie and I have been working together for several years. A little bit about Jackie. After completing a bachelor's degree at Hampshire College, she ended up, and I don't know exactly how she got there, but she worked as a bench scientist at the University of Strasbourg in France, no less. And then some years later, and this is again a fast forward, she found her way to Lawrence Hall of Science, where she has, for more than a score of years, but I won't say, I don't know how many more than a score of years, served as a curriculum developer, probably before the current project that she has been responsible for. She's best known for her works developing GEMS, Great Exploration in Math and Explorations in Math and Science. And in 2002, I think it was either the fall of 2001 or the winter of 2002, she and some of her colleagues invited me up to Lawrence Hall of Science and said they were thinking of applying for a grant to develop a new science curriculum, but they wanted to make sure that it was a science curriculum that incorporated literacy activities and did so in a way in which literacy and science served as synergistic curricular areas rather than being oppositional as they sometimes were in the earlier curriculum pursuits that went on in science and literacy. At any rate, she serves now as Associate Director at Lawrence Hall of Science and also as Director of the Learning Design Group and has direct oversight over our rather ambitious undertakings in building right now a middle school version of Seeds of Science, Roots of Reading. And she's here today to talk to us about that. Amongst the many accolades that she's received, I think probably the most auspicious is the 2012 International Society for Design and Development in Education, ISDE. She received the Eddy for that year for a program that was recognized for its excellence in design and in the educational products and materials in science and mathematics. So the project she's going to talk to us about today has received the Eddy for 2012, and Jackie is the recipient of that reward. So please join me in welcoming my good colleague from Lawrence Hall of Science, Jackie Barber.
Thank you, David. Really nice. I don't know where those notes came from, but you did very well. So, good afternoon. I'm very happy to be here. I'm planning to share, as David said, some of the work that he and I have done together around the integration of science and literacy and what we found the impact on student learning to be. I also hope, if we have time, to provide an example of how when we break out of our disciplinary silos, the productive tensions arise and we can use those to create better solutions to shared problems. There have been quite a few lessons learned in that score that I thought I'd share. And finally, as a curriculum designer myself, whose team is comprised of many GSE graduates, I hope to give a little glimpse of curriculum design as a career direction. And hoping that those of you who are interested in it will stay in touch, and because we have a lot of different projects going up at the Lawrence Hall of Science. David said that we've been working together since, I think it's 2003 that we officially started working together, or 2002 we had the fateful lunch. This was before the broad recognition about the importance of language and literacy in the context of science. And working with David on this topic at the beginning, I accrued some dirty looks from some of my colleagues at the Lawrence Hall of Science who thought I was going over the dark side of learning science by reading. And I guess I would like to say that a salient thing about David's and my partnership is that we have very different, and I would say complementary, expertise. And the second thing is, rather than David being the literacy guy on my science team, or me being the science gal on his literacy team. We actually have a 50-50 mix of people who consider themselves literacy educators and folks who consider themselves science educators. And I really contend that this equal mix of individuals with diverse perspectives really led to solutions that neither group would have come up with on their own. David mentioned our initial motivation was to set out to create a combined science and literacy program. And this was to deal with the crowded and disconnected curriculum. I had run in 2000, 2001, just as we were starting to see fewer elementary teachers teaching science. We ran a bunch of focus groups, and in talking with elementary teachers, what we repeatedly heard is, if it can't do some work for me in reading and writing, then I really can't make much time for it in the classroom. So my motive was very simple: need more time in the school day for science, and just to allow what we know works best, which are an opportunity for deep dives into the content. And David, I now know that one of his little mantras is literacy is a domain in search of content. And so he was happy to look for a context within which students could be taught to read and write and talk, where there was some motivation and purpose to what was going on there. So that seemed pretty simple, straightforward, and our tactic was we were going to make this combined science and literacy program that was all science, 100% science, but about half of the time kids would be doing things at 2nd, 3rd, 4th, and 5th grade that would count as bona fide literacy instruction in the classroom. So, okay, we could do that. We would provide kids with some experience that let them do science, hands-on experiences. We would provide them some related read, write, and talk experiences. And importantly, as I've learned from David and our literacy colleagues, provide instruction for how to read and how to write and how to talk in the context of science. So it seemed like we can do this, but we discovered pretty quickly that it was harder than we thought. There are a lot of different ways that you could combine the doing, the talking, the reading, and writing. There are different orders, different emphases that could happen, different degree of relatedness between things. And so we embarked on what ended up being a couple years of iterating and successively trying different combinations, different orders, different forms, different degrees of relatedness between the modalities. The first-hand experiences we have down from years of creating what I now know was first-hand dominated science, not a nice balance of science and other modalities, but some wonderful science. And indeed, why would you want a science program where kids aren't having the chance, especially young kids, with a chance to engage with the natural world? So we're doing okay there. In contrast to the first-hand experiences, we began to identify second-hand experiences, and in this realm we were very influenced by Anne-Marie Palinsar and Shirley Magnuson. And by second-hand experiences, we and they mean learning from others' first-hand investigations. And text is usually one of the ways that scientists share knowledge, and typically the second-hand learning experiences that we set up involve reading. And we reached for an authentic use of text so that kids were reading as scientists might. So learning from the work of other scientists, referring to reference materials, hearing about disagreements between one scientist or another, that kind of thing. And again, I've made a couple references to, we all know about the literacy wars and the math wars, and I think we're growing out of them, but in the day there were the science wars of the science that was mainly hands-on dominated with some talk to make sense of it, versus the science that was mainly reading about it and writing in the form of answers to the questions at the end. And the field has really moved towards more of a merge between all those modalities. But at the time, and in hindsight, I didn't really realize that we were trying to reclaim reading for science and appreciate reading as a form of inquiry. Fast forward, we discovered there's no one right order to do talk, read, write. When you put them in different orders, they serve different roles, and that's fine. The biggest challenge we found was one of coherence. What we found that worked best for us is identifying tightly paired first-hand and second-hand experiences. And the key to their being tightly paired is they're having a shared purpose. So you have an authentic need for both some first-hand investigation and some second-hand investigation to accomplish something. So, example, kids examine sand grains up close with magnifiers, and they see different shapes and colors of the individual sand grains. And then when they go to read a book about a sand scientist who shares inferences about how you can use the observations you make as evidence about the composition of the sand, the age of the sand, etc. Then kids are very intrigued and motivated to read about this because they've discovered the need and wondered why sand would be different colors. So that's an example of tightly paired first and second hand experiences. So science education is full of lots of doing, some of it anyway, and learning is cool, and the kids enjoy looking at sand and they enjoy reading the book, but the bigger question is, why do we conduct investigations in science? Why would we have kids be doing that? And we investigate the natural world in science in order to make more and more accurate explanations about the world. So as such, the purpose, or what we consider the key enterprise of science, is engaging in constructing explanations and engaging in arguments. And the purpose of the doing and reading we want kids to do is they're gathering some evidence that they can then muster as they try and make more sense of the natural world. So in the case of the sand activities, the purpose of finding out about the sand and reading about a sand scientist is to be able to use that knowledge to make their own inferences to identify mystery sand and what its composition is, etc. So they construct an evidence-based explanation about where their sand came from, and they're able to justify their explanation with evidence as an argument. And these are the kinds of written and oral discourse that we've had kids make. And these are, I think, 3rd and 4th grade here on different units. And just a note I mentioned earlier, that we don't assume that students know how to engage in this kind of writing or this kind of talk. And so the curriculum provides kids with explicit instruction in how to write explanations and arguments, provides language for them that they can use, and sentence starters. I think this because, my evidence is, what do you think is the best explanation? How do you know? How could you be more sure? Those kinds of things. And kids, as young as 2nd and 3rd grade in our class, are taking claims and searching for evidence that they think best matches those claims and starting to make their own explanations. And finally, we have built in many opportunities for the class and for the individual students to reflect and make sense of what they've been doing. And we named this need since in the effort, particularly in science, to cover so much ground, reflection is something that often gets left out. So what you see here is what we call our design shell that we use in our curriculum. And we think about it in different ways. That you choose a central purpose. This is about a week of instruction. Choose a central purpose. And you have maybe 2 parts first-hand explanation, tightly paired for 1 part second-hand investigation, and offering them real opportunities for them to engage in written and oral discourse there with plenty of reflection. Different ways that we've thought about this. And this has done a tremendous amount, this framework, for us to provide and promote the coherence that we were finding a challenge to bring to the curriculum. And connect that science and literacy where the literacy is serving as a means to engage in the science. And this is in contrast to what you often see out there with, quote, integrated science and literacy, where we just add some books that kids, or some articles kids can read about science and have them write what they learned about science. And not that those are bad things to do, but it doesn't resemble the kind of synergistic and authentic use of literacy as a means to support science learning. So when we create one of this week's worth of instruction, we call this an essential multimodal experience. We have all kinds of little nicknames for that, but it's this set of essential multimodal experiences that is the basic structural part of what we create in the curriculum. And then we string them together, and that makes a unit. And again, this has largely helped us with coherence within a week. It does not solve the problem of across the weeks and how we build coherence there, but that's the subject for another talk. So back to me and David and our teams. Over time, and not too long, it really became evident that we were not just talking about a matter of curricular economy in working together to integrate, but in fact, we were integrating science with the literacy of the discipline, and that finding that this is in fact a better way to teach and a better way to learn science, and also a better way for kids to learn literacy practices when it's in the context of learning about something. So our evidence for why this is effective came about through 3 different gold standard studies that we collaborated with folks at CREST at UCLA to do. And these are studies, as you know, that don't just show that students learn what they were intended to learn over the course of the unit, kind of a typical growth from pre to post. But in fact, these were studies that employed random assignment to treatment comparison groups and showed how the treatment, in this case that was kids using Seeds of Science Roots Reading in the classroom, performed in comparison to the other approach. And in most of these studies, the other approach was business as usual, content comparable curriculum. So we would choose a situation where the standards were well aligned to our Seeds unit. So what we could expect to see is teachers teaching towards those same standards, whether they were in our treatment classroom or whether they were one of the comparison classroom kids doing their business as usual curriculum. So squinting your eyes and looking across all of these studies, we found a couple of trends emerging. First, that the students in the Seeds classrooms always outperformed the control students on measures of science conceptual knowledge and science vocabulary. So that's something that happened in all the studies. That Seeds students always performed equivalently or sometimes higher than control students on measures of science reading comprehension and of science writing. And this was despite the fact that teachers in the Seeds classrooms, on average, spent less time in literacy. And the reason this was so notable to us is one of the big reasons why schools and school districts need to reserve the 2 or 3 hour chunk of the literacy block is because if we don't, our kids won't be learning in this very critical time to read and write. And so what we were showing is even when teachers took time from that block and used it to present our science, which also had literacy within it, that the kids did always as well and often better. So that was pretty exciting to us. And then another finding that we were excited about is that in the Seeds classrooms, there was more student-to-student talk significantly that we found, and that just seemed like such a great indicator of a more robust learning environment where kids are engaged in talking about and making sense about what they're doing. And this isn't a completely fair comparison here, but we figured out our this is for science learning, our average effect size across the 3 different studies. And we compared that to the average effect size reported in various meta-analyses. And of course, they had many more studies than us, but just a little bit to see that this was with one 8 to 10 week unit. We were seeing a really nice effect size. And we were excited to find that the advantage holds for ELL students. This was a population that was of particular interest to us. Marco Bravo, who used to be here at GSE, came and joined us for his postdoc, and he was focused from day one on ensuring that our curriculum would meet the needs of English language learners. And so in a smaller study, we found that the English language learners in the treatment classrooms did better than the English language learners in the control classrooms on science conceptual knowledge and science vocabulary. And I always like to give just a little bit of a feel. This is a sample of student work from a 3rd grader, Javier. And this is his writing sample before he participated in a 4-week, so 20 session, Seeds of Science Roots of Reading, the Gravity and Magnetism unit. And Javier was in a summer program for students at risk of retention. And here's a month later what he wrote about what he knew about forces. And he'd been immersed in learning about forces, different kinds of forces every day. He was reading about it, he was doing first-hand investigations about it, he was engaged in a lot of talk about it and engaging in arguments as that went along. And just to show you, yes, Javier's work sample was nicer than many of the others, but just to show you that he's not an outlier, I wanted to show you the results of our students' science writing measure, and this was for 3rd and 4th grade students for the light energy unit that we have. And this slide shows the writing performance of just the bottom quartile of readers. So we took just that bottom quartile, and you can see that that both the treatment and the control students were given an open-ended prompt to write to, and they were given that before and after the unit. And then we scored their writing based on 6 different dimensions. The strength of the introduction, the use of evidence, overall clarity, strength of conclusion, correct use of the science concept, and use of science vocabulary. And these bars show the % growth between pre-test and post-test. And the green bar is the % growth for the business as usual, and the gray bar is the % growth for the seed students. And this is just, the last bar is the sum of all the 6 dimensions, and those are the other 2 dimensions. So I'm very excited about how the curriculum appears to impact students, but also the feedback that we're getting from teachers is extremely positive. Feeling like we're helping to solve some of the problems they face with such a congested and crowded curriculum. Let's see how we're doing. I thought I'd share a little bit again on the reflections of our journey. And I guess the first thing to say is that it was uncomfortable. And I mentioned earlier that David and I, and this was one of the smartest things we did, but we brought together folks who identified differently. You know, half of them identified as science educators, half as literacy educators. And we had very similar goals in the science and literacy. You can see here, I love this list. It's actually on page 7 of the Common Core Standards for ELA, the list of student outcomes there, but very similar to what we're looking for in science. But we use, as a matter of course, different tactics, that we're very accustomed to different tactics. And so that the nature of the disciplines we were coming from were different enough that it took us a while to really kind of figure out how to bridge that gap. And there were things that each of us thought and did that were sort of an affront to what others thought and did, and it just felt wrong. And so I put a few examples up here, but there are others. I think one of the big ones is the science educators really liking open, immersive versus structured and explicit instruction. Science educators privileging first-hand experience, where the literacy educators were privileging evidence from text. Vocabulary, it took us a long time to see eye to eye on vocabulary, where those of you who are familiar with lots of how science gets taught, especially middle and high school, it's lists of vocabulary that kids need to memorize, the definitions for, etc. And I remember we worked with Freddie Hebert on this, and she started out and said, okay, what are some of the words that you want students to know? And everyone on the science side are like, oh my gosh, what have we gotten ourselves into? Until we learned more, and I'll share that in a bit. Beginning with exploration versus preparing students for exploration. The level of scaffolding that has felt comfortable, and this, which we get every time we go out and talk to science educators. Do you do your hands-on before the reading, or do you do your hands-on after the reading, etc. So the first thing we did was to seek out the synergies, the things we saw in common, and to capitalize on those. And we identified these as moments in the curriculum when students were engaged in, could be engaged in both science and literacy at the same time. And so fast forward to 3 synergies that we found and we focused on. The first is when it comes to sense-making strategies, it turns out that we use many of the same ones in science as in literacy. So in both science and literacy, we're searching for a preponderance of evidence, and that's different than in mathematics, where you're looking for the right answer. So this is a similarity. It turns out that inquiry strategies we think are pretty darn close to comprehension strategies, or close enough that we actually capitalize on this synergy by choosing one to focus on in a unit. For instance, the second grade SAND unit, we chose inference making. So kids are taught explicitly how to use inference making to make sense of the text they're reading. They are taught explicitly how to use inference making in doing first-hand experiences, and we even have some meta-level talk. How is it the same when we made inferences before we read and then look back and revise our inferences partway through our reading as when we did it when we're looking at the sand, that kind of thing. So that was our first synergy. Secondly, and this is, I told you about the vocabulary instruction being a sore point initially. It turns out, though, when we sat down and talked more deeply about what it means to know a word, to each of us, that the typical ways that we science educators were thinking about for vocabulary instruction was just the tip of the iceberg. And what our literacy colleagues considered, colleagues considered to be gaining vocabulary knowledge, but they didn't stop there, that they went much farther and much deeper into learning what a word means. And then when they pulled out this, we're like, oh, that's what you mean? Yeah, we agree with you on that. This rich network of words is the goal that they were working towards, that kids would have this, to build this mental model in their head. So not just understand what it means, what dissolve means, but understand how that relates to heat or cold, and how that relates to what a solution is, etc. And pretty soon, the more we started talking, we realized that we science educators had been mistaking not so good vocabulary instruction for rich and deep vocabulary instruction. And so this we called our second synergy, and that is realizing that there's not a huge difference between building conceptual knowledge and building word knowledge, and that the words are merely the labels for the concepts. And once we could accept that, we were all gung-ho behind constructing the same kinds of experiences to really immerse students in learning concepts and the labels for those concepts. Finally, as science educators, we're always talking about the authenticity. So we were asking questions, well, when and why do scientists read and write and talk? And this is when we started working out, when do they? And we got more and more comfortable and with the idea that really science is a large, big D discourse that involves different ways of thinking about evidence and making sense of data and a way of talking and a way of finding out about the world. And all of these things, all of these ways of being this part of this discourse of science is really a much fuller, richer, deeper way of understanding science. And this quote, I don't know if you've seen it, but love this quote. And I think it really captures what has become our team's expanded view of science. And I'm happy to say that finally, there are science standards that agree with this now broader definition of science. So what used to be in the National Science Education Standards or most state science standards are really a big focus on the central role of inquiry. And there's no mistaking it. Inquiry is certainly one of the most important practices of science. But acknowledging the importance of the social construction of knowledge, of how we talk about and negotiate meaning in science, that's where the literacy is key. And really, the last decade or more, as we've been working parallel in the field and partly through David's participation, the field has really developed a broader understanding of what it means to prepare students to be successful in science. I don't know who has read the Reading Between the Lines study, the ACT-sponsored study, but it provides dramatic evidence of this, that students who aren't capable of reading and comprehending complex disciplinary texts weren't advancing in science. So if you look at who's doing well in science ACT tests and who's doing well in reading ACT tests, they're 95% of the same kids. In other words, if you couldn't make sense of the science text where you're receiving a lot of your instruction in school, then it makes sense. You're going to fall behind in the science. The Shanahans, Elizabeth Moji, David Pearson, Cynthia Greenleaf, and others have really done a wonderful job. And I'm not going to go much into it, but if you aren't head into what's happening with disciplinary literacy right now, I really recommend doing some reading and for what this group of researchers are characterizing as the literacy skills you need to be successful in a particular discipline. So we were doing okay on the synergies, and for a while we tried to ignore the differences, the big gap, and this led again to a lot more conversations. And in hindsight, I really see that in some ways embracing those differences has led to more breakthrough for us as two groups of thinkers. That, or at least as important as finding those synergies and capitalizing on those. So here again are these different tactics that would lead to these tendencies, would lead to disagreements about how to create the instructional sequences. And I'm going to share with you, squinting my eyes and looking back, because we eventually have come to quite a high degree of agreement, what I think each group, the group of literacy educators and the group of science educators in the team have brought to the curriculum. And David, I haven't showed you this slide yet, but in general, I would say that our literacy team members brought highly intentional, thoughtful instruction to instruction in practices within the curriculum. And so we see this, that there were no assumptions made about whether kids would know how to read science texts or engage in science talk or write a certain genre of science text. Never that assumption, but some explicit instruction for how. An intentional build over time. And I often think in science educators, we have good moves, but this notion of a build over time, over weeks, over the year, is something that our literacy colleagues have really done a lot of thinking through. This notion of a gradual release of responsibility, thank you, David, which is something that many of us had naturally done sometimes in science, but really came to understand and rely on that. For those, the I do, we do, you do degradation that happens there. Instructional routines. I kept looking. The literacy instructors knew how they could pick up any book and kind of know how to go about working with students on that book. And all these instructional routines, and I'm like, wait, we have those too. So for instance, I could stand in front of any group of kids after they're having collected data and run a really good discussion about the data that they collected. And so taking a page from their book, we really started to articulate and define those instructional routines in science as well. And then finally, the metacognitive reflection. The literacy educators who were part of our team were really great at helping, making moments in the curriculum for kids to step out and talk about what good readers do, what good listeners do, and helping to explicitly name some of the things, some of the dispositions and practices that we want kids to engage in. And so as I was thinking about this, I really feel like we, as a group of science educators, have benefited a tremendous amount in how we approach instruction to practices. And so as one example, it's typical in a science curriculum for us to just immerse kids in practices, right? So they're going to be observing and recording their data and making sense of the data, et cetera. And there's some instruction, some scaffolding, but it's something where we assume that they're going to learn some by doing, and then we can guide it a little bit. And so we started doing what the literacy folks had done, which is thinking across the year and thinking when we are going to explicitly introduce kids to different inquiry practices and different science practices, and using that same notion that we're not going to assume that kids just catch on to them. We're going to immerse them in all of them, yes, because we want them to be engaged in rich science experiences, but we're going to, over the course of time, make sure that kids get some instruction and scaffolds and gradual release of responsibility, et cetera, of that. So that's a difference. And on the science side, I really think that our team, the science folks, have brought some student-centered approaches to conceptual learning that really stretch some of our literacy team members. So just as some examples, less front-loading. We don't really have to pre-teach so much. That it's okay to encounter a concept before you have a word for it. So the notion of identifying a bunch of vocabulary ahead of time isn't always necessary. Creating an authentic need to know. Really thinking through the authenticity of it. And we've actually done some focused little studies showing that we always have what we know anyway, but that engagement for students is highest when it feels most like science, the reading and writing and talking that they're doing, and when there's an authentic reason to know or to share or whatever. So when they're not aware that they're, okay, now it's the literacy time, I'm going to do this, but they're just trying to share what they found out or whatever. And finally, I think that the science group's really good at showing how to engineer focused deep dives into content, and that takes students to the how and the why in addition to the what. And I think that sometimes there's a trade-off for breadth versus depth, and if you have to choose one and not the other, always go depth is our motto on the science side. So this is, I guess, some examples of the ways in which I think the designers in the different disciplines have helped. So a second point, differences across our team didn't just come from different disciplinary background, but actually came from different professional orientation of the members of the team. So, for example, how do different members of the team define what is rigorous? And with the diversity of expertise, we have a wide variety of people. We have ELL experts and assessment developers and curricular developers and folks who are strong special ed and content knowledge, etc. But what I found is that no matter what the mix of expertise that folks had, and even though we were all engaged in design, generally people self-identified as a researcher or a designer or a practitioner. That was really, I'm this first. And what we found is that each of those roles sees ways to solve problems in different ways. And so these are questions that come up in all design projects and that we struggle with. And I find that the person who identifies as a researcher or a designer will really have different reactions and thoughts about how to proceed for each of those. Very interesting. If you look in the dictionary, we're back to rigor now, of the different definitions of rigor, it includes the quality or state of being very exact, careful, or strict. Thoroughness, the difficult and unpleasant conditions or experiences that are associated with something. And so what I find is when it comes to rigor, the researchers, the designers, and practitioners each bring rigor, but they bring a different rigor to the task. So for instance, practitioners push for others on the design team to be rigorous in insisting that we deal with classroom realities, such as attending to the timing of the lessons and their parts, material needs, as well as the need to meet students where they are. I find that researchers typically bring more rigor to the type and quality and quantity of evidence we need to draw conclusions, and those who primarily identify as designers are focused on aligning practice and goals. Very concerned with that alignment that's happening there. So some conclusions. Embrace broader definitions of science to include reading, writing science texts, and engaging in science talk. And we're really in a lovely time in history, in science education, and for that matter, in literacy education as well, that there is some mutual understanding that our disciplines aren't as narrow as they were once defined. Science educators take a page from literacy educators related to instruction practices. Literacy educators take a page from science educators related to conceptual learning. And my favorite little finding is good things happen when we break out of our various silos. And I really am convinced that we created something together that neither of our groups could have created separately, and really have expanded the ways we think about moving forward. So those are some lessons learned from the curricular and research work that David and I have been working on. Questions? Yes?
First of all, thank you for a wonderful talk. I read the Secondhand article, and focused on the adolescent literacy in specific disciplines. Your study deals with, have you studied the adolescent population from 8th to 10th grade? I'm just curious.
We are working right now in extending to 6th to 8th grade. So a little bit. Is that the population you're working with?
Yes, I'm having culture shock because one of my 8th grade classrooms, 50% of the class is reading 3 grades below. So I'm starting to participate twice a week with learning specialists to teach kids how to read text. And so it's very fulfilling and exhausting. And it really resonated. I'm developing more instructional practices where, as a classic science instructor, I like open-ended inquiry, but doesn't work in reading necessarily always. So.
Yeah, interesting. I'd love to talk more with you about that. The differences between elementary and middle school have been fascinating, and differences in both the context, the teachers, the students, the expectations of the standards in terms of the quantity of content that we expect middle school students to be able to grasp. So,
yes, I had a related question to that. So I was thinking about in elementary school and then like the transition into older grades, the idea of like who is a scientist. And I think that at younger ages we have an easier time like authentically embracing any construction of a scientist and really valuing students seeing themselves that way, and like that anything that feels like an experiment is an experiment. And then as you get older, some of that kind of gets shut down in students, and I think some of that is like institutional and some of that is possibly internal. And I was thinking especially in relationship to vocabulary, and that I think there is this idea of how you talk as a scientist. And so I was curious if in your development you talk to colleagues at the Lawrence Hall of Science or other places who really view themselves as scientists, and how you could get students to also be seen by them as scientists, not just by their peers, and the role that like literacy and the correct vocabulary plays when they want to move outside of the classroom and be scientists in a larger context, like knowing that we might like agree that they are scientists, but we're a little bit like, but you're not really a scientist. Like scientist looks, and I'm just curious about that.
So I'm not exactly sure I understand your question, but
Sorry.
I definitely understand the issue that you're talking about. And what it brings to mind to me is the Shanahan article, and I forget the year of it, but say it again?
2008.
2008. What was fascinating to me in that is that they followed around, I think it was a theoretical chemist and a mathematician and an historian, and we're looking for the authentic reading practices and finding differences in how they approach the text, etc. I think that what's been really interesting for us in working with middle school teachers is to share with them that we read, in different disciplines, we read text differently. And that's something that their students don't know automatically, and that's something that they can engage with. And so, you know, in terms of when we call students scientists and the authenticity or not of that, and how we're preparing them to be in a scientific setting or not, you know, I think I'm not quite sure the best way to measure that.
Yeah.
But was that your question?
Yeah, I was thinking about like especially discourse practices and that we might have that help students be really confident and really capable when they're still in a classroom setting, but translating that to be recognized by people outside of the classroom as equally authentic science, and for students to see that in themselves. And to me, some of that does seem tied to literacy and language and discourse, and how like the curriculum may help with that.
Yeah, I would say that one of the biggest things we hear about from elementary school teachers is the nature of their kids' talk. They're like blown away by well, my evidence is, and those kinds of things coming from little kids, and that we get a lot of feedback about that. Also, the vocabulary instruction, that they not only take on the words of science, but they take on the language of science. We do a lot with sentence frames, etc. And in our work with middle school, using some of those same techniques. Also, we just got a whole set of explanations back that kids, actually there were technically arguments that they had written, and we're looking through them, and we had given them some of the phrases that we use when we talk about data and those kinds of things. And they had picked those up, and it was really extraordinary to look at these. And it looks like they didn't do it themselves, except for we have boxes of these that come from all these different classrooms. And you can see, I can see the phrases that they were given at various times and how they appear. So I don't know. And I don't know if that's a better question for high school or,
Yeah.
I don't know.
Thank you.
Yes?
I'm trying to remember from your slide in which you showed the improvements for seeds/roots. It seemed like a lot of them were about science reading comprehension. Was the control group, did they get science instruction, or was it general reading sort of instruction?
Let me see. I can get there. The control group was using business as usual science. Some of it was hands-on science, some of it was text-based. It was the full gamut.
Right.
And we were at this study was like in 85 classrooms, and so they're all getting science about the same concepts. One with business as usual, which the teachers were more familiar with, so that it's a little advantage to the teachers and in the comparison group. But the seeds teachers had our integrated approach that they were using. And it's interesting because these are elementary students, and the time has to come from someplace, right? There's zero-sum game there. And so, indeed, we found that the seeds classroom teachers, yes, spent longer on science, but it was at the expense of their literacy block. And yet we were looking at literacy practices at the end and science knowledge at the end.
But the slides before this, the measures were all about science reading comprehension, if I recall.
This is,
Yeah, it's an earlier slide.
This.
Yeah, that one.
Yeah, so science conceptual knowledge,
Right.
science vocabulary. So those are the things that we see consistent and significant change on.
So I guess the question I have is there a chance, because they were spending more time on science and literacy, that they weren't doing as well in other literacies? Like narrative is usually something that occurs in science. You won't read and then Einstein turned to Max Planck and said, "No, your dad's ugly," or the photosynthesis haiku. Is there a chance that, although this looks like a big win, is there a chance that other literacies were?
That's a really good question. In the places we checked, our first study we were really happy because the science reading was significantly greater as well. We weren't doing science writing in that study. But what we found is sometimes it is, sometimes it isn't. And our hypothesis is that it takes, I'm getting to your question in a second, it takes longer, we believe, to move the needle on reading comprehension than an 8 to 10 week unit. So that's one thing. But again, we never saw, of the things we looked at, that the kids did less well on those literacy things. But yeah, who knows? Could have been. Yes?
You talked a little bit about the sentence starters.
Yeah.
How you getting into them. Can you point me in the direction if I wanted to read more about that?
Sure. Yeah.
Is there resources online or big lists? I'm mostly just interested in what other kinds of sentence starters there are and what we're.
Yeah. We have 81 strategy guides that we call them that are associated with 81 we wrote the children's books for these units because we couldn't find sophisticated science written at accessible language, and so we wrote them ourselves. And for each book, we have a strategy guide that features a strategy, and I'm pretty sure that we have some there. And if you go to scienceandliteracy.org and search for strategy guides, you can see what's there.
So you,
Go ahead.
they're too different from actual, like, what you find in scientific discourses, so a lot of them, like the actual little starters?
Yes.
Okay.
For the talk relates to what I'm interested in terms of a rubric for scoring the student's open response. Is there a separate rubric for English language and then one on science? If there is, what are the things that you look for in each category?
Yeah, we let's see. We score the work for, what is it? 6 different things. So it's the same piece of writing. We'll go through and look at the strength of the introduction, the extent to which they use evidence, the overall clarity, the strength of the conclusion, the correct use of the science concept, and the use of science vocabulary. So sometimes you'll see that kids are using the right science vocabulary, but the science is wrong. And you sometimes see the reverse. That you don't see much vocabulary happening there, but they're really explaining it in a way that's correct. Likewise, on the argumentation, that they could be making an evidence-based argument there that's wrong. That's based on some assumptions that they use that were not correct. So we looked at all 6 of those separately, and there's some interesting correlations that we found. In general, when you understand more about the concepts, you do better on other things. So we have a little study if you'd like to see it on that. And right, and this wasn't. We've shared this with teachers, but we wouldn't expect teachers to score one piece of work necessarily 6 ways.
Like there's a special student who writes very well and argues like for this very well, but the argument is wrong. Like literacy is good, but the science is wrong. How do you balance it? Would it just be grading those 6 areas separately, or?
Yes, we look at them separately, and that does happen. And so we have a bunch of look-fors in the work, and then what next? And so depending on where kids need more help. But ultimately we would want the argument to also be correct, but these are kids who are learning how, and we think that even if it's incorrect, that you can see that they're able to muster an argument.
Thank you.
Yes.
So it strikes me that in both science and in writing, that revision is a really important part of both processes. And so in our work, we work in science inquiry, and we always have trouble motivating students to revise their ideas and to see that as this essential part of the process and not just this annoying assignment that they get in addition to all the other assignments they get. So I was wondering if you had any like instructional approaches or ways that you encourage revision of ideas.
I can't say that we do. And when it comes to all of the science learning goals we have, and then all the literacy learning goals we have, we have a very constrained instructional space. And so we make some choices about what to include and not, and to the great upset of our literacy folks, we have revision as something that you can do, but it's not part of the main trunk, just because everything takes so long. And so there are, I think that teachers and classrooms where that's a classroom practice and do it, will do it. But we haven't really gone there as a team, so when you figure out what they are, you'll have to tell us, and we'll put it in the curriculum.
All right.
Yes?
You talked about how there were some advantages to different orderings of the cycle that you were
in a science audience, you often get, oh my goodness, you couldn't possibly have kids read before they do. You have to have them do before they read. And because they do not want to eclipse kids' discovery, and they didn't want to have it turn into something where it's a verification, where I read something and then I do it and see it. So we never do that. But what we found is there are legitimate roles for text, no matter where it falls with respect to other parts of instruction. So if kids are reading a book first, that isn't so much information delivery, though certainly some does, as much as a context setting. So for instance, in a unit on properties, what is a property and why do kids want to learn about properties? So we actually have a little book that David helped write, which is why aren't rain boots made of paper? And it's a whole book that's sort of playful, that in which the kids in the book compare the properties of substances and the uses of substances and come up with some comical matches. And at the end of that book, kids understand what a property is, so they have a early working definition of what a property is, and they see that the properties of the material you use to make something matters, based on a bicycle out of bananas, books out of sugar, those things there. So in that case, we've found text is a really good way to set a context for something that's bigger and outside of the classroom, and maybe connects to the field. I might even say the authentic analog to that is, if I'm a scientist who's going out to do some work, I would see kind of how it fits in the field and what someone else has done, etc. So these context-setting books are things that we use often, not always, but often in the curriculum. And in that case, I think text is a better way to set context than a first-hand experience. But if I'm looking for kids to have the experiences that you would have in doing something firsthand, before they, for instance, have words introduced or whatever, we would want to do that first. So I think our takeaway was any order can work, but the modality might play a different role depending on the order and what your goals are. And interestingly enough, so we have a whole framework for roles for our texts, and we found it translated perfectly to roles for videos. So as we're involving more multimedia in our middle school program, same thing, the different roles of setting context, delivering information, serving as a model, offering new data that kids can make sense of. Those kinds of roles you can do with multimedia or with text medium. Any other questions?
All right. Thank you
Wonderful.
so much, Jackie.
Thank you very much for spending the afternoon.